Okay, we're going to start the next and the final part of the symposium, the afternoon session in Iran, and I guess the morning session in the rest of the Western Hemisphere. So it is my pleasure today to introduce to you Peter Zeidman, who is a Senior Research Fellow in Wellcome Center for Human Neuroimaging in UCL. He is currently working, one of the colleagues of Carl Friston, and he actually introduced Peter to us, which we're very happy to basically learn about his work. Peter is one of the main developers of DCM, I guess both conceptually and also mathematically in this SPM software package for analysis of Fmri data. He has basically interests in his neuroscientific interest is mainly is in hippocampus and in investigating the neurobiology of memory and perception in healthy and disordered aging. And prior to that, for his PhD, he was working on high-resolution functional neuroimaging of hippocampus with Professor Eleanor McGuire. And we are very happy to have him here today to teach us about the potentials of DCM, I assume. And with that, I guess, Peter, the floor is yours. If we can just one more time check your voice, because we don't have your voice. Okay, good.
Thank you for that lovely introduction, Ali.
Sure.
And just to check, you can see that slide okay?
Yes, we do see the slide and we hear you. Yes.
Great. Well, it's really lovely to be here. Thank you so much for the introduction and for the invitation. This talk is going to be about mathematical modeling, and in particular how we can use modeling as a mathematical microscope to investigate the biological mechanisms that give rise to the neuroimaging measures that we collect. And everything I'm going to talk about, all the technologies, we make freely available in the SPM software. And that's a toolbox for MATLAB, and also it works with the open source Octave package if you don't have MATLAB. And my role within the SPM team is that I develop, as Ali was saying, tools and technologies for modeling neural circuitry. But actually quite a lot of my work is trying to demystify and simplify a lot of the statistics that goes into SPM and try to help people to implement and understand it. So that demystifying is what I'm going to try and do a little bit of today. And in particular, I'm going to focus on what are called inverse problems. Now, I know some of you may have an engineering background, so you might be very familiar. Let me just quickly clarify what an inverse problem is. And it's actually something quite ubiquitous across different areas of science. And I think a nice analogy for what we do in neuroimaging is actually geology. So a geologist, I'm not sure, can you see my cursor if I move my mouse around?
Yes, we do. We do see
fantastic. I'll just switch that to point of view, actually. There we go. So a geologist may be interested in processes that are deep under the surface of the Earth, which cannot be directly observed. However, what they can do is specify models that say if the dynamics behaved in a certain way, these are the vibrations we would expect to measure at the surface, and in turn, these are the measurements we would expect with a seismograph. And then, having specified that generative model, a generative model means it's a model that can generate predicted data. You can then run that model in reverse and ask, given the data that I've observed, what's the most likely underlying processes that would have caused my data? And that's called model inversion. We have a very similar challenge in neuroscience. So the processes that we're interested in might be the activity of particular kinds of synapse, might be their time constants, for example, or it could be the averaged activity of many neurons as a neural population. And again, at least in humans, we cannot directly observe this. But what we can do is specify models that say if there were particular changes at the synapses, this is the change in electromagnetic signal or bold response we'd expect to be exhibited, and in turn we can specify models that say this is how we'd expect those physiological processes to turn into measurements using Fmri or MRI or EEG or MEG. And again, we have this difficult inverse problem of starting with the data and then asking what's the most likely set of underlying neural parameters. And that's the challenge I'm going to be talking about today. I'm going to split this talk into 4 parts. Firstly, I'm going to ask what makes a good model. And I'm going to answer that from 2 perspectives. One is statistics and the other is machine learning. And I'm going to try and highlight the commonalities and the difference between those 2 perspectives. And then going to talk about how we actually assess models in the SPM software, and that's using something called Approximate Bayesian Inference. So those first 2 parts are going to be lots of theory, and then I will say thank you for staying with me for all the theory by then moving on to some empirical examples. And I'll talk about multimodal neuroimaging and computational psychiatry. Okay, so what makes a good model? There are many, many different answers to that, but I'm going to try and answer that from a statistical perspective. And I would suggest, although I'm not a philosopher, the point of science is to come up with incrementally better and better stories or explanations for what caused our data. And that's what we do over the years as we publish more papers, is we refine our narrative. And when a story or an explanation is stated in a precise way, then we refer to it as a hypothesis. And if we state it using the language of mathematics, then we refer to it as a mathematical model. So from a statistical perspective, the quantity that we use to quantify the goodness of a model is referred to as the model evidence, also called the marginal likelihood. It's the probability of having observed my data given a particular model, say model 1. And you can imagine that if the data looked exactly like what my model would have predicted, then this value would be larger. Whereas if the data looked nothing like what my model would have predicted, then this value would be smaller. So you can see it's a score for how good the model is. And a model here could be anything. It could be a regression model, or it could be some incredibly complicated biophysical model, and I'll show you some of those later. Now, usually we don't just talk about the evidence for a single model. That's not so informative. Usually we have at least 2 hypotheses, and we want to compare them. So typically you'd have what's the probability of data given model 1 divided by the probability of data given model 2, and that's referred to as a likelihood ratio. And that really is the critical quantity in evidence-based science. The likelihood ratio, the relative evidence. In classical statistics, examples would be t-tests, f-tests, and in Bayesian statistics, what I'll talk about today, the likelihood ratio is called the Bayes factor. And it's a really critical quantity. To just try and make that specific, a little taste of what I'll talk about later. Let's say you had 2 hypotheses for how the brain is responding to a task. And in each hypothesis, you've got 4 brain regions shown by these circles. In hypothesis 1, it's possible that the task is modulating 2 connections in that network. And then you might write down an equation that represents that hypothesis. In fact, in practice, the software does the equations for you. You just have to tick some boxes. But in principle, this is what is happening. And you might have a different hypothesis that the task only modulates 1 connection, which causes activity to flow down another connection here. And you might have a different model, a different equation to represent that. So to arbitrate between those 2 hypotheses, we would then compute the probability of the data given model 1 divided by the probability of the data given model 2. And if the Bayes factor was, say, 20 times the evidence for model 1, I might say that's really strong evidence in favor of this hypothesis. What I'd like to talk about now is why we use the model evidence and why we use that to quantify the goodness of a model rather than any other quantity. And the reason for talking about that is because I notice increasingly that certain quantities from machine learning are being used in papers to test hypotheses. Quantities like classification accuracy, decoding accuracy. And so I think it's important to be aware of the relative advantages of each of the different kinds of statistic that maybe sometimes gets missed. So why use the model evidence firstly, before we come to machine learning? Well, the first reason, I'll give you three reasons. The first reason relates to what's called Occam's razor. And Occam's razor is the principle that the simplest model is usually the best. To explain why using the model evidence helps to satisfy Occam's razor, I firstly just need to introduce Bayes' rule. Now, I know for some of you this is very basic statistics, but I just need to introduce this for anyone who isn't so familiar. This formula is the very fundamental core of all of Bayesian statistics. And it describes the relationship between our knowledge before doing the experiment, our prior, and our knowledge after doing the experiment. That's the posterior. So let's say we've got a model with some parameters theta. Theta here is a vector of numbers. It could be regression coefficients for a regression model, like an ANOVA, or it could be connection strengths for a connectivity model, a neural network. It doesn't matter. So we've got these parameters called theta that we can't observe, but we want to try and infer. Before doing my experiment, the inputs, the things I have to decide as the experimenter, are the prior and the likelihood. The prior says, what's the probability over the different candidate settings of the parameters? Which parameters values do I think are possible? Which do I think are impossible? That's the prior. M here is the model. The likelihood is you think of that as a mathematical function that says, given a particular setting of the parameters, how probable is it that I would have observed the data that I've observed? And depending on which model you use, that will determine the likelihood. You'd have a different likelihood for a regression model versus a connectivity model. So that's the inputs. Together, the likelihood and the prior form what's called the generative model. The outputs of Bayesian modeling are these two other quantities. I've already introduced the model evidence. That's the probability of the data given the model. And that's a score, as I said, for how good the model is. The posterior is what I should believe about the values of the parameters after seeing my data. So it's what I've learned from my experiment. Which particular parameters are big, which are small, which are positive, which are negative. Okay, so now back to the question I'm asking. Why should we use the model evidence, and why does it help us to comply with Occam's razor? Well, if you rewrite Bayes' rule, you just rearrange the symbols, and you take some averages, some expectations, then you can rewrite the log evidence, the log of the model evidence, in terms of the accuracy minus complexity of the model. Accuracy is how closely do the predictions of the model match the actual data. But that's only half the story. So the accuracy of a model isn't enough to tell you whether a model is good or bad. You could have a bad model that's highly accurate. What actually matters is the trade-off between accuracy and complexity. Complexity is defined as the divergence. This is called KL divergence. It's a measure of distance between what the prior probability over the parameters and the posterior. In other words, how much have you learnt by doing your experiment? And a really good model will be highly accurate, but it will have very low complexity. It'll be very simple. And that's a good explanation for the data. So automatically, if you compare two models based on the evidence and select the better one, you are automatically selecting the one that gives the best trade-off between accuracy and complexity. Okay, that's number one. Number two is something called James' principle of maximum entropy. If we take the log evidence, and again...
Okay, Peter, I think we are back online. For some reason we had a...
Okay, fantastic.
Yes. So just
to say...
Yeah, this is slide.
Fantastic. And if that happens again, please let me know verbally, because my slides are full screen, so I can't see the messages while I'm talking. The take-home message from the slide is when you select between two models based on the log evidence, you're naturally selecting the one with the higher entropy, and that's a good thing because entropy is another way of saying that it's the smoothness of the posterior distribution. So by choosing the model with the higher evidence, you're naturally choosing the one with the smoother posterior, which is illustrated here. You would select this light green one instead of this dark green one. And that's a good thing because it means the model is simpler and more likely to generalize to new data. All right, so those are two reasons, closely related: Occam's razor, Jane's principle. Third reason why we use the model evidence to compare models is something called the Nyman-Pearson lemma. And this is a fundamental proof in statistics. And it's something that we use when we're deciding which of multiple models, multiple statistical tests is the more appropriate. So when we're doing a statistical test, we're trying to trade off two competing priorities. One priority is that we want to minimize the number of false positives, the type 1 error or alpha. But the other thing we want to do is try and keep the power or the sensitivity of the test as high as possible. And those two things are not compatible. The more conservative you are about false positives, the less sensitive or less powerful your test will be. So the question is, where do you draw the line between where you're going to believe the null hypothesis and where you're going to believe the alternate hypothesis, to use the language of classical statistics? That critical value, it's proven by this thing called Nyman-Pearson's lemma. That critical value is optimal or optimally set when you set it based on a likelihood ratio, like the one that we've just seen, the Bayes factor. If you set your criterion for what you believe based on a likelihood ratio, then for any given alpha or false positive rate, you have provably the most powerful inference that you can make. And that's the reason, it is this proof that is the reason why people use t-tests, f-tests, Bayes factors. This is really critical. And what it means is there's no other test that you could possibly invent that would give you a higher power for any given false positive rate. And that should be a critical consideration when deciding what to use to draw your conclusions. Should I use a Bayes factor, a t-test, or should I use something I get from machine learning, like a classification accuracy, which is not based on a likelihood ratio? The Nyman-Pearson lemma tells you that that classification accuracy statistic, or any other statistic, must be equally powerful as the Bayes factor or less powerful. So those are three reasons then why the log evidence is a good measure. Or just to say, we often take the log of the evidence because it makes the mathematics a bit more simple. So why would we use the log evidence? I've given you three reasons, but where does that leave machine learning? And what I'd suggest is that the log evidence isn't the whole story. It's not enough just to show your model is better than another one. We also need to show that it's useful in the real world. And I'm going to draw here, I'm going to try and draw a divide between two different aims. The first aim for modeling is hypothesis testing. I want to know which model best explains the data. And I've made the case that the likelihood ratios are good for that. In other words, Bayes factors, t-tests, f-tests. The second thing is where machine learning comes in. And we can ask the question, are the inferred effect sizes that I can get from my model large enough to actually be useful? So for example, let's say my model was inferring whether there's a difference between patients and controls in a data set. I would test that hypothesis using a likelihood ratio, a Bayes factor, a t-test. But the second question then is, okay, I've got this model now that can detect that difference. Could I actually use it to find out if somebody has got the disease, if they are a patient or are a control? Could I use it to build an AI to make that distinction? So what you can then do is what's called cross-validation, and I think what you should do, which is to say, it is to train your model on some subjects. And now ask the question, if a new subject's data comes along, can I predict whether they are a patient or a control? And the formal name for that is out-of-samples correlation or out-of-samples testing, also called cross-validation. And really good modeling papers in neuroimaging tend to have both of these two steps. They first use the statistics to test hypotheses, and then they test the real-world application by using a kind of machine learning approach to ask, can I use my model to predict something about new data? You might also ask, is there a formal relationship between these two kinds of quantity mathematically? And the answer is yes, they are in fact equivalent. Let me give you the take-home message first, which is that if you choose the model with the higher log evidence, you are likely to have the model that is going to generalize better and do better at machine learning. I'll give you the technical detail now, but if this is too much technical detail for you, then just have a rest for a minute. In the formal language of statistics, prediction is stated in terms of something called the posterior predictive density. It says that the probability of observing the data from our new subject, that's our test subject, given the data from our training subjects that we've trained the model on, is equal to, essentially this is Bayes' rule. We've got the likelihood times, not the prior now, but the posterior that we got from the training data. So we take what we learned from the training subject and multiply it by the likelihood for the test subject, integrated over the parameters. I called this theta before for the parameters. I've now called it beta. Doesn't matter. So that's a formal way of stating prediction. And this probability you get back is a prediction for that new subject. And it's helpful to turn that into what's called a predictive score, which is just a number that says how good the prediction is. And the statistician called Good in 1952 suggested taking the logarithm of that probability. So what you get is a negative number, and the more positive that negative number, the closer it is to zero, the better your prediction. And why am I telling you that? Well, finally, if you were to sum that predictive score over different sizes of training and test sets, so over different numbers of subjects who are kept behind for the training, then you get the log evidence. In other words, the log evidence is equivalent to what's called leave n out cross-validation, where you average over all the values of n. So that's the formal equivalence between the two. And I'll just repeat the take-home message of this again. If you choose a model between models, and you select the one that has the better t statistic, the better f statistic, or the better Bayes factor, then your model is probably also going to be better at prediction. Okay, so that's the first part. Let me just summarize what I've said so far. So in neuroscience, we tend to infer quantities we cannot directly measure. And that requires specifying generative models and inverting them. And then over time, we iteratively improve our models using what's called Bayesian model comparison. And this has a few advantages that I set out. It optimizes the trade-off between accuracy and complexity. It gives the simplest possible posteriors. It gives us the most powerful inferences, and it selects the models with the highest predictive power. I should also say that this Bayesian modeling can give quite surprising results sometimes, and things can be a bit counterintuitive. And if you want to read more about those counterintuitive cases, I can recommend these two papers. This is one that I'm a co-author on from a few years ago, and this one just came out last week and has some interesting ideas in it. Okay, that was part one of theory. Just a tiny bit more theory to go, and then I promise I'll move on to empirical examples. So, a little bit more theory. I've just spent 20 minutes telling you why the model evidence is a really good statistic for testing hypotheses. I'm now going to tell you that it's completely useless because it's absolutely impossible to calculate it for any real-world utility. The model evidence, I haven't given the definition of it for now. So the model evidence, probability of the data given the model, is the likelihood times the prior, that's the top of Bayes' rule, summed or integrated over all the possible settings of the parameters. For any kind of real-world model with lots of parameters in particular, there is no analytic solution to this integration. This cannot be calculated in closed form, which means we can't compute the evidence, which means we can't compute the posterior, and Bayesian inference is therefore impossible. Or is it? So the point I'm trying to make here is that although that's impossible, there is a way around this, but it requires a little bit more thinking, and it's called approximate Bayesian inference. We're going to try and find a way to approximate the model evidence so that we don't have to calculate this integral. This is what the SPM software does for you when you're fitting models to neuroimaging data. And I think it would be just a good use of 5 or 10 minutes for me just to explain how the SPM software does this so that you can understand the outputs. Now, to approximate the log evidence, there's a few different ones that are commonly used. You'll see this in any statistical software. You'll see AIC, BIC. You'll also see in SPM what's called the free energy, which is a phrase that comes from statistical physics. Or in machine learning, it's called the evidence lower bound, or ELBO. All three of these approximations are accuracy minus complexity, just like the evidence itself. And their definition of accuracy is similar. It's not identical, but it's similar across these three. But where they mainly differ is how they define complexity. So AIC and BIC calculate the complexity of the model as the number of parameters p, or a function of it. That's a really bad way to quantify the complexity of a model. And the reason is that for any kind of model that we typically use, the parameters will have some degree of correlation. In other words, tuning up or down one parameter will have a similar effect on the data as turning up or down another parameter. So the effective number of parameters is almost always smaller than p, which means that AIC and BIC over-penalize, and they can get things very, very wrong. So I would recommend in any neuroscience experiment, do not use these approximations. The free energy, also called the evidence lower bound, approximates the complexity as how far the parameters have moved from the prior to the posterior. And that is a measure that does take the correlation of the parameters into account, and therefore doesn't suffer this problem that the AIC and BIC do. And if you'd like to see a formal comparison between these approximations, this is a very good paper by Will Penny. Okay. Now, how do we define this free energy? What is this thing? And I'm just going to say very briefly, because the detail will take a bit longer than I've got. So very briefly, this is something called variational phase, by the way. It was developed originally in statistical physics by Richard Feynman, and more recently it's found popularity in machine learning in the context of what are called variational autoencoders. So a variational phase is the way it works is that we can't compute the log evidence. As I've said, it involves that integral we cannot compute. But what we can do is define a function called f, which by design will always give a number as its output, which is less than or equal to the log evidence. This is the function. I'm not going to go into detail of this, although it is reasonably straightforward, so check out the Wikipedia if you'd like to know more. But the thing to know about it is that it's a function, or more specifically what's called a function of a function, that gives whatever input you give it, it will return a number that is less than or equal to the log evidence. The input to the function is a probability distribution called Q over the model parameters. What you then do, having defined this, is then to have an algorithm that will try maybe hundreds, maybe even thousands of different possible probability distributions, and it will plug them in, and it will try to find the one that gives the free energy, that makes the free energy as big as possible. And when the free energy is as big as possible, it will be approximately equal to the log evidence. Let me illustrate that. So let's say this is the number line here. This is the thing we want. I want the probability of the data given the model. That should say the log probability of the data given the model, but I can't calculate it. But what I can calculate is the free energy, which takes this probability distribution Q as input. The algorithm is then going to search over many, many different probability distributions Q, and it's going to try to make the free energy as close as possible to the evidence. And when the free energy is maximized, it becomes approximately equal to the log of the evidence, and Q, that's the probability distribution that maximized it, Q becomes approximately equal to the posterior over the parameters. So what this means is that we can approximate the log evidence and the posterior without having to do any complicated integration. And that's what the SPM software does for you. There is a catch, and there's always a catch with these kind of things. The catch is that the mathematics for actually doing this by hand is appalling. So if you just wanted to implement the algorithm to do something very simple, just find the mean and variance of a normal distribution, it would take around about 2 pages of mathematics. This is the Wikipedia entry. And you can work through that example. It is interesting. But practically, as neuroscientists, we just want to be able to either take a model that somebody else has used, or we want to write down our own model. But we do not want to be doing pages of mathematics in order to derive an algorithm to fit each model to the data. So the solution to this is to use an algorithm that does all the mathematics for you. In SPM, Carl Friston invented the algorithm, and this is really at the core of how model fitting works in SPM. The algorithm is called the Variational Laplace scheme, developed by Will Penny and Carl Friston. You now get similar kind of packages actually in certain other Bayesian stats packages. And the idea is that you don't have to do any difficult maths. It will just fit your model to the data. Let me show you an example. I'll just briefly introduce this example, and then you can download this if you want to play with it yourself if it's of interest. Also, just before I introduce the example, let me emphasize that if you're an experimenter and the idea of writing mathematics and code is horrible to you, please don't worry at all. We have models that are suitable for EEG, MEG, Fmri that don't require any coding. They're available with a push button kind of interface. This is just to show you how it's working under the hood. So let's say that the data is these 2 time series. And you now want to evaluate the evidence for a model. And the model is always specified in 2 parts, shown here mathematically and shown here in terms of MATLAB code. The first part describes how the latent variables, the unobserved variables x, evolve over time. It's the time derivative. And this, for example, could be the synaptic or the neural activity. The second part of the model describes how the latent variables, like the neural activity, is translated into the observations that we measure using our scanner. And as you'll see later, this could be a model of the hemodynamic response that gives rise to bold Fmri, for example. So all models have these 2 parts. You have to specify those 2 parts. You have to specify priors and initial states. And that's what's shown here in this code on the right. You can see it's quite short. And then it's just 1 line of MATLAB code, and it will give you the free energy for your model. That's the approximate log evidence, as well as the model parameters. And you can then use that free energy to compute the Bayes factor and ask which model is best. Okay, so interim summary then. Models allow us to infer quantities, that is parameters that we can't directly observe. In SPM, a model is specified for each hypothesis, and then the log evidence is estimated using variational Laplace, which is an algorithm. Different models can then be compared to test hypotheses, and we do that based on the log evidence, although we can't actually compute log evidence, but we have to approximate it by the free energy, also called the elbow in machine learning. All right, I've given you a lot of theory. Let me now talk about studies. I'm slightly behind schedule, so let me just see. I'm hoping we can talk about both of these. Okay. Firstly, this is a slightly older version of the slides. There we go. It's fine. So I'm going to talk about brain connectivity first, and I'm going to come back to computational psychiatry. Okay. This was a really interesting study that was conducted by a recent master's student of mine, Claire Tack, and it's in collaboration with Rick Henson's group at Cambridge with the CAN-CAN dataset. And the question here is what changes in the brain in healthy aging, or normal aging, I should say. And in the study, which had 635 participants aged 18 to 88, participants performed a very simple task while undergoing Fmri. They pushed a button in response to a cue with the finger of the right hand. If we then do a test for where in the brain is there an effective age, the biggest effect by far is in right primary sensory motor cortex. And the response there is really interesting. So remember, they're pushing the button with the right hand, and this is right cortex. So this is ipsilateral motor cortex. And if we plot the age of the subject in years against the amplitude of the bold response, as estimated using an SPM analysis, what we find is that young people very consistently have a negative bold response compared to the baseline, which is just rest. Whereas as you get older, it's more and more likely you're going to have a positive bold response. And in the oldest people, most have a positive bold response in right M1. But there are exceptions. So you can see that there are some people here in the blue. This is just a clustering into two groups. People in the, shown in blue here are about 88 years old, and yet they still have the negative bold response of a teenager. And the interesting question that we're tackling is, why is that? What it causes these differences between people, and could there be some interesting like correlation with lifestyle or health? There's a couple of ideas. It could be neural, it could be vascular, or it could be both, or it could be neither. So how do we investigate that? Well, it should be clear from what I've been saying so far that the way we would test that is through a Bayesian model comparison. Compare models where this is explained through neural or vascular explanations. Claire used what's called dynamic causal modeling for Fmri. DCM is just that variational Laplace algorithm I showed you earlier applied to investigating neural connectivity. And the model is in two parts. The neural part is a very simple equation for Fmri that just describes the flow of activity around a network. The hemodynamic model is more biophysically detailed. It describes how neural activity gives rise to a vasoactive signal that dilates blood vessels, which in turn increases blood flow, which causes a change in blood volume and deoxyhemoglobin, and finally causes the bold response. So what Claire did was to specify models like this and then invert them so that you run the model backwards and ask what's the most likely neural connectivity and also hemodynamic parameters. So here's the model she specified, the structure of it. There were 6 brain regions shown here. The network was driven by left SMA and left dorsal premotor cortex. And we're interested in what causes the negative bold response in M1 in young people that goes away when you get older. Here are the predicted time series from models fitted to each group, the older in red and the younger in blue. And what reassuringly you can see is that the model can reproduce this change in sign of the bold response, with older people being positive, younger people being negative. So the model captured the data feature of interest. Now we can look inside the model and look at the estimated parameters, that the posterior probability distribution over the parameters, to see what caused this. So here are the parameters, the difference in parameters between two groups, younger and older subjects. In each case, there's 6 brain regions, and here are the ones that showed a difference between groups with a very high probability. And what you can see is that these interhemispheric connections from left hemisphere to right or ipsilateral M1 became much stronger as people got older. So this is a weak connection in the young people and becomes stronger. It's weak here and becomes much stronger. So that's interesting. It suggests that the interhemispheric connections might be sufficient to explain what we're seeing in right M1. The nice thing about having a model is that you can, once you've fitted it to the data, you can then do virtual experiments on it. You can perform virtual lesions, or you can just turn up and down the dials of different connection strengths, and you can see what will happen to your data features. And that's what Claire did here with an in silico experiment. So this is looking at just one connection here, left premotor dorsal to right M1. That's this connection here. And she turned that parameter up or down and showed that it can, and what you're seeing here is the right M1 predicted bold response. And you can see that that connection is sufficient to change the sign of the bold response. And in fact, any of these 3 parameters she found, increasing any of them, was sufficient in the model to flip the sign of the bold response, which mirrors the aging process. And it's important to say that none of the other of the many connections in the model could do that. Those are the only 3. The other thing I mentioned earlier when we were saying what makes a good model, it's not just the model that has the highest log evidence, but you also need to show it can predict something, or it can it has a big enough effect size to have that predictive validity. So the final part of this paper was to say, given those connection strengths that we've estimated for each subject, could we predict whether their right M1 bold response was positive or negative? Because if so, that connection is enough to explain this, this effect. So these 2 plots show the connection strength versus the bold response estimated using SPM. And what you can see is that there is quite a strong correlation between these 2 parameters, left SMA and left premotor, but actually not left motor. So only with these 2 connections was there a relationship between the estimated connection strength and the amplitude of the bold response in right M1, and the total variance explained was 44%. So our conclusion from this study was that flipping of sign of the bold response, we can explain 44% of the variance in that by interhemispheric connections. That's good news because we've done a good bit of explaining, but it also means we've got quite a lot more to explain, and that's future work. And I can just give you a taste of what that future work will be. We're going to be using a framework here that was developed by my former postdoc Amir Hussain Jafarian, who's now based at Cambridge. And this was asking how we can integrate fMRI and MEG data or EEG data. Because for something like neurovascular coupling, if we want to properly ask if that aging effect was neural or vascular, we need independent measures. And EEG and MEG gives you a direct measure of brain activity, whereas fMRI gives you a measure of hemodynamic or vascular activity. And we want to try and separate those out. And the idea here is to specify a single generative model that can predict both kinds of data. The neural model here is one that we provide out of the box with SPM. It's standard. It's what's called the canonical microcircuit, and it encodes the cortical column by 4 populations. And we use the EEG or MEG data to fit the model. In other words, to estimate the time constants of the synapses. The new part then is to have weights that go from each population to a weighted mixture that then drives a hemodynamic model, which then predicts the fMRI data. And we fit this part of the model to the fMRI data. And the key thing by having both data is that we can estimate these parameters in the middle. The weighting, the contribution from each of the 4 populations to the bold response. And it's our hope, using multimodal MEG fMRI data, that we can then drill further into this, this change of sign with aging and get a formal Bayesian model comparison to say, is it the neural parameters, is it the neurovascular, or is it the vascular parameters that can explain that change and those differences between people. All right. I haven't got much time. There's only 10 minutes. So I'm going to now just very quickly give just illustrate a very different study, but that uses exactly the same algorithm. So what I just showed you, use the variational Laplace algorithm, that's all built into DCM. I'm going to show you that same thing applied to something quite different. This is a collaboration with Francis Jin and Roman Kotov. Francis is based in Hong Kong and Roman is based in the States. And this is asking the question of how do we infer a psychiatric disease process that we cannot directly observe, and it's continuous over time, but we can measure symptoms at regular intervals. How do we infer the disease process from the symptoms that we measure? The data that is available here is a large sample of patients with psychotic disorders, and in particular, they got ratings for psychosis, mania, and depression over a 4-year period. It's just binary. They either do or do not have each symptom over those 4 years. And the aims here is to develop a model whereby we could classify patients based on the dynamics of their underlying pathology. In other words, trying to create diagnoses and classifications based on mechanisms, not on symptoms. That would also enable us to do forecasting, to be able to say when is someone's symptoms going to come back again. That would be the real dream if that became possible. And this is just a first step, a proof of concept. Here's what the data look like: psychosis, depression, and mania in 9 subjects. And you can see here for some subjects it's a bit cyclic. So this person had a bout of depression and then another one. Some people have this cyclic kind of pattern. Others may just have a single episode of a symptom and then it resolves. So some variability there across people. I won't write out all the mathematics of the generative model, but I'll just give you the key variables. So here we've got exogenous input. So that could be life events, which you can try and code up based on surveys if you had that available, which causes some change in the person's neuropathology, which in turn causes a change in the psychopathology. And finally, the psychopathology, for example, the presence of mania, gives rise to a symptom score that is binary. They either do or they do not have it. So here symptoms are treated as a consequence of the underlying neuropathology. And I'll just focus on where the most interesting stuff is happening, and that's this level of the model, the neuropathology. So let's say we've got 3 variables, x1, x2, and x3, that summarize that person's neuropathology. These could be 3, you think of these as 3 principal components. You could also think of this as 3 brain regions that may be involved in the disease. Or it could be 3 neurotransmitters that may be disruption to those neurotransmitters cause symptoms. And a patient forms a particle who is on a trajectory through this neuropathological space. What we're interested in is the dynamics or the trajectory that that patient is on. Are they on a cyclic kind of trajectory like this person is, or maybe they're on a linear trajectory? And we can parameterize this in a very broad and generic way using what's called a Lorentz Attractor, which is just a very generic way of modeling dynamics. It comes from fluid dynamics and weather forecasting. Their position in that 3-dimensional space then goes through a linear mapping to translate from the disease space to the psychopathology space, and then that gets binarized to create the symptoms. And again, we use that same variational Laplace algorithm to estimate the parameters here. And let me show you, for the 9 exemplar subjects, the estimated quantities. So here's mania, for example, and this is the exogenous input. So this is estimating life events that may have intervened at those times. Here's the pathophysiology, the Lorentz Attractor, estimated for each subject. And you can see that it's estimated that some subjects have a very cyclic disease course, like this person, whereas others are on a more linear trajectory. These variables in turn give rise to the psychosis, depression, and mania, and these are the expression of those 3 pathologies over time. And then just off the bottom here, I haven't shown is binarizing those 3 symptoms. So hopefully this gives you a flavor of what's possible as a way of trying to formally understand any kind of longitudinal disease process. This is only a proof of concept, and as we get further down the line, we'll put tools in SPM to make this kind of modeling easy if you want to apply this to different kinds of disease. Very, very briefly, and it's the last couple of minutes now, it's very important to validate models, and I could give a whole nother talk on model validation. This particular model it's just a nice way to illustrate different ways of validating models. So here we validated it in 3 ways. One is to determine whether the parameters are identifiable. In other words, we use the model to generate simulated data, simulated patients. And then we fit the model to the simulated patients, and see if we get back the parameter that we started with. And that was indeed the case for this quite important parameter that controls the dynamics. A second kind of validation is a confusion matrix. In other words, asking, can we identify models? So here we imagined there were 9 different kinds of disease, 9 different sets of parameters. We generated simulated subjects from each of the 9 groups, and then asked, could we identify which group they came from, using Bayesian model comparison. So for each subject, we fitted 9 models, compared the free energy, and see which was higher. Generally, this worked, although you can see that there's one group here, group 8, that was hard to identify and was regularly confused for some other groups. But overall, this worked well. And I mentioned the third thing is predictive validity that we always try and do. If we leave out a subject, can we diagnose them? Are our effect sizes big enough? And what you're seeing here is the ground truth labeling for 2 groups, 0 and 1. And here's the estimated parameter. And you can see there's a very clear separation. For each left out subject, each new subject, we could predict which group they came from with a very high out of samples correlation. So it has predictive validity. Although I must emphasize it is just a proof of concept. There's probably too many parameters in it, and it does need some more refinement. But hopefully that gives you a flavor. All right. Now my summary slide was in the wrong place. Let me find my summary slide. There it is. Summary. Thank you so much, firstly, for listening. I know that was an awful lot of theory and a lot of equations. I want to summarize by saying that to properly understand a system, we need to test hypotheses about its underlying mechanisms. The evidence for different hypotheses can be optimally evaluated using Bayesian model comparison. In other words, comparing models based on their model evidence. This is complemented by assessing the model's predictive validity using cross-validation and other methods that come from machine learning. And these are 2 complementary aims. And finally, SPM provides tools for model inversion, in particular an algorithm called Variational Laplace, and we have out-of-the-box models for Fmri, MEG, and I should say EEG data. So with that, I'd like to say thank you particularly to Carl Friston, from who I've learned almost all of what I have explained, my collaborators listed here. And some further reading I can recommend, and sorry, I've just realized Rick Henson and Ethan Hunt at Cambridge should be listed here as well. There's some further papers here if you're interested in some further reading. This one is about using this kind of technology in psychiatry. The second one is about inferring neurovascular coupling. And the third one here is a basic, complete beginner's introduction to dynamic causal modeling. And I've got another paper coming out in a few weeks, I hope, which is a tutorial on the variational Laplace scheme, explaining all the mathematics as clearly as I could. And I'll leave you with this very nice quote from Richard Feynman, which I think is a very nice motivator for doing modeling. He said, "What I cannot create, I do not understand." And I think that's a nice phrase. Okay, thank you very much.
Okay, thank you very much, Peter, for the interesting and educational presentation. So if there's any questions, please type it in. So I see some questions, or at least one question. No, well, I think this is from the time that you got disconnected. So yeah, so if there's any questions, please type it in, or raise your hand, and you can have the mic for question and answer. While people are thinking about asking questions, let me ask one question about one of the data that you showed. The x-axis was the level of connectivity, and y-axis, I forgot what was it, and there was an R-squared about 50% or something. Remember that? But the 2 groups, right? This one, exactly. This. So when you look at this data, you can clearly see 2 clouds of Gaussian, which probably I assume that corresponds to those young and like the 2 groups that you showed, the red and blue. So within the groups, I don't see that correlation. It looks like what really drives this correlation right now is the difference between the 2 groups being separate from each other. I'm sorry, I can't hear you. I think you're.
Sorry, I was muted.
Oh yeah.
That
Okay.
is a very good point. Yes, I think that really this is just validating that what you see in the what you see in the SPM derived data, just the overall amplitude of the signal, corresponds to the strength of the connection. So as you say, this very big difference between the two groups, you would expect them to be concordant, and that certainly does drive it. Absolutely.
Okay, but looks like within each group, the connectivity between, let's say, PMD and M1 might not really.
Yeah, that kind of looks a bit flat, right?
Yeah.
And that looks a bit flat, whereas this looks a bit more angled, maybe.
Right.
Yeah, no, I think that's a really good point. I never actually tested the correlation within each group separately.
I see.
And I regret that you didn't review my paper, because I think that would have been a really good thing to have tested.
Yeah.
So that is a very good point.
And one other thing that I wanted to mention is that initially when you were talking about the probability of y given m, I was a bit confused, but now I totally understand what you mean, because most of the time when we do the basically likelihood ratio, we do the likelihood of the data given the theta of the parameters. Like we have a bunch of parameters, and we fit the parameters to the data, and we find the likelihood of our data given the parameters, which is different from what you're describing, which is like P of y given m, and that is integrated over all the parameter of space, which as you mentioned correctly is a very good thing to have. But since we don't have it, then you use the variational base to try to fit it. Is my understanding correct?
Your understanding is perfect. Yeah. So I mean, if we decompose log evidence into accuracy minus complexity, the accuracy is the log probability of the data given a specific setting of the parameters. That's called the likelihood. And so for any kind of maximum likelihood estimation, you're just getting this bit. So that means you have to, if you're doing any kind of difficult inverse problem, you have to find some way to regularize the solution in order to penalize complexity. And anything you can do in Bayesian stats, I should emphasize, you can also do in classical stats. So in classical stats, you can do something like a ridge regression. You can do a regression where there is a penalization term for complexity. The thing with those is, however, they're a bit like a fudge factor. Like, they're not elegant. Those factors are usually just put in to make it work. Whereas the nice thing with Bayesian statistics is you can derive from first principles that complexity penalization. So it's certainly more elegant, although you could in principle achieve it with both kinds of methods.
And this formula that you wrote is exactly the same as that F free energy, right?
Yeah.
This is accuracy minus complexity.
The slight difference, there's a slight difference. So complexity, when you're talking about the log evidence, is how far the parameters have moved from the prior to the posterior. With the free energy, we have the approximate posterior. It's not the real. It's not the real one. It's a simplification.
True.
But the principle is the same. It's how much have I learned in terms of information in units of nats. Actually, is the unit. How much have I learned is from doing my experiment.
And the Laplace variational thing is slightly, I assume, is a different way of approximating the whole thing. The method that you said Carl has developed.
Yeah, so I mean, so as I mentioned, in fact, now in a lot of the different packages, JASP and others, there are Stan is another package. There's convenient ways of doing this kind of doing the variational phase without having to do maths. In other words, it makes certain approximations. The way it works in algorithm is that it just implements this and quite a broad class of models. And that class of models is that Q has a normal distribution. The log joint has a normal distribution. Does anything else have it? There's normal distributions all over the place. So essentially, if you are happy with those approximations, those assumptions, then then it works very well. I mean, I'll say what the disadvantages are, maybe, which is that, firstly, any variational Bayes approach has a bias towards too much confidence, so too high a precision. and that is standard for all variational Bayes approaches. So the estimates it gives you will be slightly over precise on average. And the other thing is this does involve making assumptions. So the whole point of the variational Bayes, what allows us to calculate this when the log evidence is not calculable, is that this Q is a simple distribution. It's simpler than the real one. And for example, as I said, in SPM, this is going to be a normal distribution. That simplification is good a lot of the time, but sometimes it's not good. So if, for example, your model had a posterior that was very bumpy in shape, so you couldn't describe it by a normal distribution, now it's not going to work so well.
I see. And this is so assumption of jointly Gaussian between y and theta and Gaussian Q is the basis of the what you call variational Laplace Bayes. Is that the difference between general variational Bayes and what you describe as Laplace?
Absolutely. So this on the left here is general variational Bayes. But when you actually want to come to use this, now you've actually got to plug in values for P and Q. And it's the decision on what to plug in.
I see.
Yeah.
Okay, very good. So questions for Peter. So this the way Peter broke it down was very good. Part of it review and part of it new for myself. I guess everyone. So don't be shy. You can ask any questions. Oh, so we have Dr. Rashid Shamali, please.
Hello. Thank you very much for the nice talk. I have one basic question, and that is the concept of temperature that we have in free energy in physics, in statistical physics. How you can assign the temperature for neural data? What is the same concept that you assign temperature in neural data?
That's a very interesting question. It is particularly interesting because I'm not a physicist, and so I actually approached free energy from its implementation in machine learning, and I'm certain you would know a lot more about statistical physics than I do, I'm sure. Somewhere where temperature comes in, and again, I've had to skip an awful lot of detail on this.
The difference between energy and free energy is what temperature makes less than the total energy.
Yeah.
And so to neural data, and I'm wondering what is the temperature here that you call it free?
I'll give you two answers to that to see if either of them are useful. And I need to have the James principle. Right. So this is a decomposition of the log evidence, but you can also do the same decomposition of the free energy into these two terms. This term is often called the energy, and this is called the entropy. And that's by analogy or by metaphor with the statistical physics. So the log joint here would be called the energy of the system, and then you would add on the entropy of the system. So does that help?
That is the same in free energy, but in physics, free energy have this log likelihood minus the temperature cross the entropy. That is the meaning for free energy.
Oh, okay. Yeah, so I think it must just be a different decomposition. So it must be equivalent. But I'd have to look at how it's defined, I'm afraid, to be able to answer
I'm
your
wondering
question.
about the concept. There is some assigning concept between energy and what you are talking here. Energy. Yeah.
I'm sure there is, yes. I think it's probably going to be a reformulation of this. But no, I'm really sorry. I can't answer your question because my physics knowledge isn't good enough. I'm embarrassed to say.
Thank you.
I'll Wikipedia it after we finish. Maybe others will do the same.